In a 2014 publication by the Canadian government, falls were deemed the leading cause of injury-related hospitalizations among seniors, with 20 to 30% of seniors falling every year. Falls can be especially dangerous if seniors are alone and the injury goes undetected. They may be unable to call for help to either a family member or caretaker. A team of 4 undergraduate engineering students have attempted through a term project to collect sufficient data to develop a machine learning model to solve this problem. The goal of the project was to construct a model to detect when a person has fallen in an indoor environment from a color image. This model would allow healthcare workers to be notified when a fall occurs for quicker intervention and to prevent undetected injuries. Machine learning is a suitable approach as it is a binary classification problem to predict whether or not the individual has fallen. There are extensive images of fallen and standing individuals to serve as data for the model to be trained, validated, and tested. The team used a dataset of 9,079 samples to train the machine learning model, collected from fall dataset. The images in the fall dataset were RGB images with dimensions 320 by 240 pixels and had 6 classes. The 6 classes in the fall dataset were empty, standing, sitting, laying, bending, or crawling, with 14 different individuals in various indoor environments.
For the purpose of this project, each of the individual's images were first separated and placed into only 2 categories, fallen and not fallen. The classes of sitting and empty were not used in the final clean dataset to allow for simpler predictions. Images in the class standing were labeled as not fallen, and images in the classes lying, crawling, and bending were labeled as fallen to allow for only binary classification, rather than requiring the model to classify each of these physical positions. The split of data was approximately 80%, 10%, and 10% for training, validation, and testing respectively. When splitting the dataset, we ensured that a room or person was not present in more than one set to prevent overfitting in training or overtuning hyperparameters from the validation results. A balanced data set with respect to labels ensured that when checking the validation and test accuracy of the model, it reported an unbiased accuracy representative of both labels. There are 12 individuals in the training dataset and 1 individual in each of the validation and test sets. The team built several models over the course of the project, including an SVM to use as a baseline, a CNN as the primary model, and a CNN which classified AlexNet features to compare with the primary model.
The limitations of the baseline model became evident quickly. Despite removing color from the images and generating a histogram of oriented gradients, the baseline model struggled to classify the data and achieved an accuracy of only 49.8%. We expected this due to the highly complex nature of both the data, including variation of color in the rooms, different viewing angles, and different body types, and the simple nature of the linear SVM. The preliminary model was a 2-convolutional layer CNN with a 2-layer fully connected classifier. This model architecture was chosen because it applies well to image classification tasks, and our spec did not include a need for orientation detection. The team experimented with modifications including dropout and adding another convolutional layer. However, this was unable to meaningfully affect the results of the model, as the validation and test accuracy remained consistently low, meaning the team needed a new approach. Quantitative results of the CNN model were that it had extremely high training accuracy of nearly 100% and high validation accuracy of 91%. However, accuracy on the test set was significantly lower at only 54%. Qualitatively, the team believes this was due to the dim lighting in the test set images. Both of the images displayed have the fallen label, although the model did not predict image A correctly. Image A originates from the test set, which had a low accuracy, and image B originates from the validation set, which had a much higher accuracy.
So the final model was an AlexNet convolutional neural network, which uses AlexNet to extract features from the images resized to 224 by 224, specifically identifying a person in the image. Since AlexNet is a widely used general image feature extractor, it generalizes pretty well for finding people. Our model was given these feature maps, and the convolutional layer was able to focus on the classification from the extracted features. 2 models were built using different hyperparameters, competing with one another, and the final was chosen, which had 8 epochs of training. A very low learning rate was used with an atom optimizer for the robust heuristic it provided in practice, as opposed to SGD. The model uses one convolutional layer, taking 256 AlexNet features as inputs. It uses padding to ensure information is not lost on edges. There is a fully connected layer for classification, with 0.4 dropout to prevent overfitting. Binary cross-entropy loss is also used with a sigmoid at the end, since this is a binary problem. Quantitative results of the AlexNet model included performing very well on validation and test sets, which contained well-lit images that were representative of lighting conditions in the training set. The validation accuracy is 94%, and the test accuracy is about 87%. Some qualitative results of the AlexNet model was that similarly to the CNN model, it didn't perform as well in rooms with dark or dim lighting. The previous test set from the CNN model was experimented with on the AlexNet model, which received 64% accuracy, still a 10% increase, but it still wasn't being able to predict images similar to A. So over here, we're going to test our model on the holdout, never before seen set. And on the left, we have a not fallen example from the holdout set. And on the right, we have a fallen example from the holdout set with about a balanced data set. Here we go for the demo. I just loaded the holdout set from the drive, and we have 1,058 images. Now let's plot around 12 of those, see how the examples kind of look like in the holdout set. So we can see here we go, some people standing, falling, etc. Now let's take the 14th index of the holdout set and see how the AlexNet features get generated for this. So we see a person standing over here, and maybe this vertical bar represents them. So that's pretty cool AlexNet feature extraction. Here are the only first 14 because there's too much to plot. 256. So here I load the features of the AlexNet, and here's our model. Now for the final test to see if we can get a good holdout accuracy result. And it is 87.15% and a 0.27 loss. Very respectable results and almost compares to the testing. So very nicely resolved.
The rate of false positives is 1.6%. False positives do not pose a significant risk, but could be seen as an inconvenience for falsely alerting caregivers. However, continuous false positives could cause caregivers to not take an alert seriously. The rate of false negatives is 23.7%. False negatives could have a significant impact as the fall would go undetected and may result in serious injury with delayed response time.
The team believes that the false negatives are originating from the images in the bending class, which is when the person is in the transition stage between standing and fallen. In this example, the model only incorrectly predicts the bending image, which means the model could eventually detect the fall when it is visually more evident. In conclusion, the final model only works well with brightly lit images and when the individual in the image has clearly fallen and is not in the midst of falling. As a team of undergraduates, we have attempted to solve this important problem, although further modifications to the architecture and more data can improve the model's versatility and robustness.